as a hand where we can understand a good part of the story, but leaves plenty of room for mystery, creativity, and discovery during this period. And that's, I think what makes, this is the period that makes cosmology exciting today. So this is what I was calling last time, at the beginning of the course, classical cosmology. And as we move in this direction, we're talking more about contemporary cosmology. What are the big issues in cosmology today? Yes?
So if, say, BICEP detected gravitational waves or something, where would it bring the yellow line?
You wouldn't know. So the gravitational waves don't tell you where they were, how they were formed. There are theories that would predict that they would, the inflationary theory would say they predict they would have been formed at this time. But that is a hypothesis, it's a story of hypothesis, which you'd want, if you wanted to be confident that's true, you would have to be independently verified by, more tests that convince you that inflation is the right story. We do see the density fluctuations, and those are also, in the inflationary paradigm, predicted to be produced at this time. So by this time, I mean somewhere between 10 to the minus, a little bit below 10 to the minus 42, more like 10 to the minus 35th seconds. I guess this diagram is somewhere like over here. But we'll also talk about theories which say, actually, they're on this side of the story. They could have been produced then, and that in fact we actually never reach this unification scale. Something happens here more dramatic, so-called bounce, and then actually they're formed back here. So that's just an indication of the fact that when you see fluctuations, although they're often presented to the public and to the scientific community within the context of a theory. If you're thinking about cosmology, you really don't want to assume the story. You want to ask, what do you observe? What can you learn directly from what you observe, independent of the story? Because you may have the wrong story. And that's very much the case at the present time. It's quite in doubt as to what is the correct story. That will be a lot of the subject of the second half of the course. So this period, no changes, and this is also the period which we call lambda CDM. So, when people talk about the lambda CDM model, they're talking about a model that we described before, in which we assume the dark energy is a form of cosmological constant. We assume that the dark matter is some sort of cold dark matter. That's what the CDM means. That the cold dark matter is the dominant form of massive particles, the mass that makes up the universe today. We assume that there's no change in the laws of physics, and that general relativity, Einstein's general relativity, is valid. And that story fits the observations back to this point. But, as we'll discuss at the second half of the course, while if you accept all the assumptions of lambda CDM, you can explain everything up to the present, it requires very special conditions to have existed at this point. And those special conditions cry for an explanation. And that explanation has to lie somewhere back here. That's where ideas like inflation and bounces and alternatives come in. So lambda CDM is not a theory in the sense of an explanatory theory. It's a theory where you put a lot of stuff in, special choices of parameters already designed to match up with what we observe, and it just shows that story is a good descriptor. It's a parameterized model. It's not a theory in the sense of a deep explanation of why things are the way they are. For that, you need to explain what those special conditions. But it says if you give me those special conditions, I don't need any new physics to explain anything up to the present. It doesn't explain or say anything directly about the past, other than we need to provide those conditions. And it doesn't tell us exactly what's going to happen in the future. Lots of options on both sides. And that's what we're most interested in. Where did everything come from? Where is it going? So the most interesting questions are not answered by lambda CDM. It says there's a little window in the story which we understand well. And it puts tight constraints on any imaginative idea you might have about the universe. it really ties things down, illuminates lots of possibilities that people have speculated about over the course of human history about the evolution of the universe. A lot of that is eliminated by what you know here, but there's still freedom, lots of freedom on this side and this side. And those are the most interesting questions, in my opinion, yes.
Is the most constraining piece the zero curvature?
No, it's a set of things. You mean the conditions that you need here?
Yeah, like what's
No, it's a lot. It's a whole list. I don't want to jump ahead in the books. Yeah, we'll talk about that. Okay. Most of the evolution of the universe during this period, so when we're talking about past the Planck epoch, is boring in the sense that it's just the universe expanding and cooling. And it's expanding at a rate that's expanding adiabatically. Entropy is conserved, just as cooling and expanding, okay? But there are interesting periods along this history where some interesting things occur. And I've already pointed out a few, but we want to highlight some of those now. And these will be periods, for example, among these are periods where adiabaticity is no longer, is not satisfied. Deviations from adiabaticity. Sometimes small deviations, small productions of entropy, sometimes exponentially large productions of entropy. Those will be the periods where interesting events that we want to focus on. So before we focus on deviations from entropy, let's first of all talk about deviations from adiabaticity. Let's just talk about adiabaticity. When is it valid? So we're thinking about particles interacting with one another, and we're asking when are those interactions, when can they be treated adiabatically? And the answer is simple. It's when the collision time is short compared to the age of the universe. So there are many collision times for expansion time. So the collision time is given by 1 over n, right? So I'll tell you what these different parameters are. N sigma v, and we want to know what that is compared to the age of the universe, which is h2 minus 1, where I'm leaving off constants of order unity here. So the n over here refers to the number density of the particles in question. And their number density, we're asking when things are expanding. When is the universe? When is the adiabatic approximation valid? And in an adiabatic approximation, if it's valid, it means it goes as 1 upon the volume, or 1 upon a cubed, or I can write it as t cubed, because in adiabatic expansion, t goes as 1 upon a, and we'll be most interested in, for most of the history of the universe is, in terms of this graph, is radiation dominated. So I'll be talking principally about events occurring in the radiation dominated epoch. And in that case, I know in terms of time units, t goes as 1 upon a goes like t to the 1/2, so this goes like t to the minus 3/2. The particles are colliding with one another with a cross-section sigma, and it'll be important for this analysis how sigma depends on temperature or energy. So sigma, cross-sections generally depend on energy, have some energy dependence, which means they have some temperature dependence, which means they have some time dependence. And that will depend upon the particular nature of the interaction. If we're talking about the radiation-dominated era, primarily, then the velocities, typical velocities, are going to be relativistic, so we can treat v to be of order 1. If RAD, radiation domination. Okay? If the universe is radiation dominated, typical velocities are going to be relativistic.